Hello. Today we're going to be learning about related rates, a very important real life skill. When doing related rates, the first thing you want to do is create a sketch of your problem. This helps you visualize and identify your variables. The next thing you want to do is write an equation to express the relationship between your variables. Next, you want to take the derivative with respect to time. Next thing you want to know, substitute the known values, find your answer, check your answer, make sure it's reasonable. Here's a scenario. Imagine you're just chillaxing when all of a sudden Godzilla starts invading the city. Okay? Big, scary monster. And naturally, he's unstoppable. There's no way to fight him. He's got big laser breath. Very, very scary, very big. Alright. Now, naturally, the army's going to be like, we're going to have to do something about this. So, imagine that the military begins loading supplies, right, to provide for the people. After 1 hour, they have assembled supplies at a rate of 150 feet cubed per minute. And imagine it in this scenario, they're putting it into a perfect cube-shaped structure. Right, this is where all their supplies go. Now, the side lengths of the cube are moving outwards. This is where our sketch helps at a rate of half a foot per minute. So that's how fast these are moving outwards. We need to know what are the lengths of this cube. So now we can find the lengths of the cube right here. So, because this is a perfect cube, we want to find our equation, which we know for cube can be written as volume equals x cubed. Because we need to know the rates, we would like to take the derivative. So when we derive this, it effectively just becomes dv over dt. Right, it becomes 1, and then you just have that left over. And then we are left also with, on this side, with 3x squared dx over dt. Taking that variable with respect to time. So now we have some known values, right? We have the rate at which the volume is increasing, and we have the rate at which the side lengths are increasing, which is what these values are equal to. So we can now substitute the known values. 150 is equal to 3x squared times 1/2. And now we just need some good old-fashioned algebra. We should find that you can multiply by 2 to get rid of this 1/2, which gives you 300 on this side. Right, so now 300 equals 3x squared. Then we would like to divide by 3, which will give us 100 on this side, x squared on this side. And then we can now square root to get rid of that square to leave us with 10 is equal to x. So we were now able to find the side lengths of the cube. Beautiful. On to the next one. Now, imagine another scenario. Naturally, Godzilla is going to be doing crazy stuff. Okay, now imagine he throws a car at you, right? You're going to need to know how fast the distance between you and the car is, right? So we'll say that Godzilla throws a car at 55 miles per hour towards you, and we say that your speed, max speed when you're sprinting away from this car, is 14 miles per hour, right? So we have our known values, and we would like to know how fast the distance between the car and us is decreasing. Right. First, we want to write a picture, right? So we'd say Godzilla's here, and this could be our distance. We'd say that we are over here, and the car is over here. So, if we want to find this length, we want to do our distance, which we can say A, minus the car's distance, which we can say is B. So the distance can be written as A minus B to get this distance. Distance, perfect. So now we would like to take the derivative with respect to time, which this one's quite simple because everything is just gonna just go to their rates. Beautiful. And now we're going to take our known values, 55 and 14, and put them in here. So we have 14 minus 55, which will then tell us that it is equal to negative 41 miles per hour, which is the rate at which the distance is going. It is decreasing at negative 41 miles per hour. Okay. Godzilla, naturally being a very big guy he is, he's gonna knock over some buildings, right? So we're gonna imagine that he's knocked over the nugget, and two cars start driving away. Hopefully you're in one of them, because you can get away as fast as possible. So, one of the cars, we'd say, is going to the north, right? Up north. And they are going at, and the other car is going west, like this, right? The northern car is currently 40 miles away, and the western car is 20 miles away. Knowing that the northern car is driving at 32 miles per hour, and the western car is driving at 50 miles per hour, we need to know how quickly the distance between the two is changing. So, this is, once again, we're going to look at our picture. We're going to write the equation, which we can use Pythagorean theorem here, which is a squared plus b squared equals c squared. Alright, now we once again take the derivative with respect to time. So we're going to get 2a dA over dt plus 2b dB over dt is equal to 2c dc over dt. Once again, simply plugging in our values. We will get 2, and then we just say A is the northern car, which is going to be 40 miles away and going at 32 miles an hour, plus 2 times B, which is going to be 20, going at 50 miles per hour. And then C, solve for C, which we know would be about 89.443. We can now solve for dc over dt, which is like kind of off to the side here, around our room. And doing all of that, you'll find that dc over dt is equal to 50.982 yada yada yada. You only have to go to the third decimal place. So we can conclude that the distance between the two cars is increasing at 50.982 miles per hour, about 51 miles per hour. Alright, so now we can imagine some tanks. Alright, we have some tanks. They're moving away at 60 miles an hour. And Godzilla, 4 miles above the ground, has fired a laser at 100 miles per hour down towards the interception point 3 miles away, which the tanks are rapidly approaching. So we need to figure out how quickly the distance between the laser beam and the tanks are changing. So this can once again be expressed with Pythagorean's theorem of a squared plus b squared equals c squared. And we can once again take the derivative with respect to time. 2a dA dt plus 2b dB dt is equal to 2c dc dt. And now we're once again going to put in our known values. So we can say that c is going to be 5, and the rate at which c is going is 100. So 100. And then it doesn't matter if the tanks are A or B, so we will make it B. The tanks are 3 miles, so it'll be 2, 3, and then the rate at which the tanks are going, which is 60. And then finally A, which is going to be this one, 2 times 4, and the rate, which we don't know yet. But thanks to some wonderful algebra, we can find that the rate at which the distance between the laser and the tanks is changing is negative 80 miles per hour, which means it is getting closer to the tanks at 80 miles per hour. Right, next one. Naturally, the laser beam is going to hit at some point and lead to a big explosion. And naturally, we need to calculate how fast the volume of this explosion is increasing. So, we have our little picture, just a little sphere. And we know that it's getting bigger, it's growing. Alright. So, we need to know the equation for a volume of sphere, which is 4/3 pi r cubed. We know that the explosion has grown so that the radius is equal to 25 feet. And we know that the radius is also expanding at a rate of 20 feet per second. Okay, so once again, we're going to need to take the derivative. Because we have 4/3 and pi in the front, and they're constants, they're not going to be derived. So we're going to end up with 4/3 pi 3r squared with our rate of radius with respect to time once again. And we're going to have that is equal to the rate at which the volume is increasing. Because that was equal to the volume, and it has since become derived with respect to time. So now we once again want to substitute our known values. So we know, we can write it again down here. For more space, 3/3 pi 3. So our radius we know is 25. And we know the rate at which is increasing is 20. Perfect. And now, knowing this, we can solve to find that the rate at which our volume is increasing is going to be 10,000 pi feet cubed per second. Alright, on to the final problem. So Godzilla has fired his laser at us now. And we need to figure out how quickly the distance between the laser and us is decreasing. Which means if we need to find the rate at which this laser is increasing. We can assume that the laser beam is a perfect cylinder. And we know that the equation for a cylinder is pi r squared h, which is equal to the volume. And naturally we want to find the rate at which the r is increasing. The h is increasing, sorry. So, we know some things though. We know that the radius is equal to 10 meters. We know that the height at the current moment in time, the laser has been at the current moment in time, the height of the laser is 50. Well, the distance of the laser, which tells the height of the laser, is 50 meters. We also know that the radius is not increasing. So the rate at which the radius is increasing is 0 meters because the laser beam is not getting any wider. And then finally, we also know that the volume is increasing at a rate of about 622,831.85303 meters cubed per second. Alright, so we have our variables, we have our sketch. So we once again need to take the derivative with respect to time. So we get dv dt is equal to pi r squared dh dt plus 2 pi r h dr dt. Perfect. So we know that we don't have this variable, but we have the rest, so we are able to solve for it. And when we do, we will find that the rate at which the height is increasing is 200 meters per second. Alright, now on to the second part. We know that we are 4,828 meters away. And we need to know how long we have until the laser from Godzilla's mouth hits us. Alright? So, assuming we're running away, once again, at 14 miles per hour, or in meters is going to be 6.25856 meters per second, we can once again find out the rate at which the laser is getting closer to us. So we can just do our equation from the first problem, which a distance is our distance away minus distance the laser's away. We derive once again to find the rate at which the distance is decreasing. And we can once again plug in our known values. So we know that the laser is going at 200 meters per second. So we know that 200 is equal to our speed, which we're going away at 6.25856 meters per second. Oh, I'm sorry. I put the wrong one. We're trying to find how quickly the distance is changing. So it's like this. And we want to subtract the 200 to find that the distance is changing between us at negative 193.74144 meters per second. And we still want to figure out how much time we have left. So if we just divide this number here, we will end up with about 25 seconds.